All right, we are now recording. This is 5035 MAA tutorial week 3. Let me write it down here. So 5035 MAA tutorial 03. And this tutorial is about free damped vibrations and forced vibrations. So before we start with the tutorial, I want to give you a brief, very brief summary of the lecture. So what we have, do we have on Aula? Let me check if you have it on Aula. There should be a formula sheet. Have you seen the formula sheet on Aula?
Yes.
Yes. So you are confirming there is a formula sheet. Where is it?
The bigger one from the formula sheet on the left.
On the left?
Week 3.
You mean
If
here?
you go up there above part, there's a formula sheet, but like a full one.
Is it up or down?
It's in the session 3 tutorial. It's the fourth document down.
Oh, four documents. Yeah, there you go. I found it. I found it. There you go. Here it is. Okay, so this is what you will also have available with you. Well, the exam is a TCA, so you have all the power of the internet available, but ideally you can solve the entire exam with just this formula sheet. And as a summary, I want to try and give you this same thing very briefly here. So what are free damped vibrations? You know that vibrations happen because you have inertia and a restoring force of a spring. If you only have inertia and the restoring force of the spring, you know that if you do the free body diagram of this, we end up with the same equation we had last time, which was this one. Agreed? Now, this is the simple harmonic motion equation. This is not in the form that mathematicians like, because mathematicians like this form more. Okay, so this is called harmonic equation. This is what you have to know and what you have to remember, because many phenomena, physical and non, can be described by this equation. And the solution of this equation, remember, is just very simply x of t is an amplitude sine omega n t plus phi, where a and phi are two constants that depend on the initial conditions. So if I pull this mass up, say 3 centimeters, and I release it, this will oscillate with an amplitude of 3 centimeters. So it depends on the initial condition. If I pull this up 1 meter, then it will oscillate with 1 meter amplitude. That's very easy. All right. What happens if I include now a damping element? Now, this is called the dashpot. It's a concentrated damping element. And what happens is that, look at this. This is a sine wave. This is just a pure sine wave, which is just shifted in phase with a certain amplitude. So a sine wave never decays. This goes on forever, which of course is not what you experience in real life. Real life, all kind of vibrations are always somewhat damped. They die out after a certain time. And so if you do the free body diagram of this, so let me put this into and let me put it in black, gray, say. Remember, this is what we had in the past. Now, if you do the free body diagram of this, you get that the equation of motion is m x double dot plus c x dot plus k x equals 0. Now, this is the equation of motion for this system here on the right. And you see that the difference is just that we have added this term, which depends not on the displacement, not on the acceleration, it depends on the velocity. So the first derivative of the displacement. Why? Because these kind of dashpots, these elements, these damping elements, the way they are built, okay, make so that they are dependent on the velocity of the mass that is above. The fact that this is in quadrature, so this is if this is a sine wave, this is a cosine wave, and this is a sine wave again, just opposite phase of this. Derivative of a sine is cosine, derivative of cosine is minus sine. Agreed? So displacement and acceleration, they have the same sine wave, just opposite, whereas the velocity is shifted 90 degrees. So this puts this term here in quadrature, and this quadrature term has the effect of eating away energy from the system. Because in this case, this energy here goes into this energy here, so they just exchange energy into the spring or into kinetic energy. Spring energy, kinetic energy, elastic energy, kinetic energy. Whereas this is actually eating away the energy of the system because the damping element is heating up. So this gives eats away energy that does not stay in the system. So this gives a solution. The solution of this is, what do you think? Still a sine wave? Yes, almost. Is an amplitude times a decaying exponential term times a sine wave. Now look at this. This is exactly, well, almost exactly. If you look at this one, this and this seem they are related. This A and this A are also related. So what's added here is this term. This one here is called decaying term. Well, let's call it exponential decay because that's what it is. And of course, this term is the oscillatory response. So you have a continuously oscillatory response that decays in time exponentially. Yes.
Most of the time it's on the omega nt.
This one is called zeta omega nt. I'm going to explain these terms. Okay. In fact, I skipped one step because before we go from here to here, of course, this you can do this, but before we go from here to here, I forgot to normalize this equation. Let me put this here. Forgot to normalize this equation by the mass. If I divide everything by m, I have x double dot plus c over m. Now c over m, I don't want to call it c over m. I want to call it 2 zeta omega n for reasons that I'm going to explain now. X dot plus, again, k over m. Remember, we call this omega n squared. So this is the equation of motion. And the solution to this equation of motion is this. Now you see this zeta comes from the fact that if you have to write this c over m, this becomes a mess. This becomes much easier to write down. And also zeta has got another meaning. It's a very powerful thing because zeta is defined as the damping ratio. So terms, this C is called damping coefficient. Zeta is called damping ratio because it's a ratio of coefficients, which is the damping coefficient over a critical damping coefficient. Now this critical damping coefficient tells you if the solution is this one or it's another kind. You have three. So I told you the solution is this, but I kind of lied because the solution is this only if zeta is smaller than 1. Because if zeta is equal to 1, the solution loses the oscillatory part. And it's just an exponential decay. And if zeta is greater than 1, this effect is even more amplified. So it's decaying and not oscillating. And this happens in this way, like this. So this is x, this is t. So x of t goes like this. And this is the x. So let me put this in yellow. So this is the oscillatory part. And of course, you can also observe the decay. This is the exponential decay. So this is the decay, and this is the oscillation, of course. This is sine omega t plus 5. And Mahmoud online is asking, what is the difference between omega d and omega n? Let's go to that. As you can see, these are not the same. This omega d is not omega n. There's a reason for that. So this oscillation that you see is not happening at the natural frequency of the system. It's happening at a different frequency. So this oscillation here is at a different frequency than the natural one. So that different frequency is called omega d, which is omega n times 1 minus zeta squared. So as you can see, omega d will be the same as omega n if zeta was 0. What does it mean for zeta to be 0? Well, the only way for zeta to be 0 is to have c equal to 0, so no damping. So if there's no damping, omega d becomes omega n, and see what happens if you have no damping. Zeta times omega n becomes 0, e to the power of 0 is 1, and we are back to the original solution here. All right, so everything checks out. If you have no damping, this is still valid, and it becomes this. So this is just a particular case of the most general one, which is this one. All right, what is this critical damping ratio? Well, this in particular, it's 2 omega n m or 2 square root of km. You can imagine, since omega n is the square root of k over m, there are different ways of defining this. All these things are here. Okay? C over C critical, C over 2 omega n m, what I said. For zeta smaller than 1, this equation of motion has this solution here. I called it A, but it's the same thing. This is omega t, and I called it omega d, but it's the same thing. And there you go. That's it. That's all you need to know. One other thing that we might want to know is, since this term is exponentially decaying, that means we can get information on damping based solely on the fact that this amplitude and this amplitude, the ratio of these amplitudes is the same. So the ratio of this and this is the same as the ratio of this and this, and so on and so forth. That's what exponential decay means. So that also means that we can define the logarithmic decrement delta, which is the log. Ln means the natural log, so log in base e, of a ratio of two successive amplitudes, say an over an plus 1, and that's equal to say 2 pi zeta over 1 minus zeta squared, I believe. Check. Yes. And since we know for zeta that is smaller than 0.1, well, this is almost 1. Okay, so 1 minus 0.1 squared. 0.1 squared is 0.01. So that's almost 1. So this can be approximated to 2 pi zeta if zeta is smaller than 0.1. Right? I'm just rewriting what's here. Okay. Okay, now this is for successive amplitudes. What happens if you don't have successive amplitudes? Say I'll give you the amplitude of this oscillation and the amplitude of this oscillation. These are not successive amplitudes. So how do we solve this? Well, it's easy. Now, the most generic formula is for the logarithmic decrement is delta equals 1 over r. And instead of being successive amplitude is r amplitudes away from n. Okay, so this is the logarithmic decrement. If r is 1, if the amplitude is the successive amplitude, so the amplitude n plus 1, you put 1 here and you go back to the original definition. All right. That's it. Now we have everything we need to solve this. We didn't talk about what happens if zeta is equal to 1 or zeta is greater than 1. Well, if zeta is equal to 1, let me see if I can do this here. Well, no. If zeta is equal to 1, the solution looks like this. Okay, so it's just a decay, an exponential decay that doesn't overshoot. Okay, so it comes at rest in the shortest possible amount of time. If zeta is greater than 1, this is still overdamped, but less so. Okay, so it comes at rest in a longer amount of time. Imagine if this is very viscous. Imagine if this thing here was very, very, very viscous. You take the mass up, you release it, and then it slowly goes down. Okay. If this is underdamped, we call it, so if this is very weak, then the mass will have time to overshoot down and then up and then down and then up, and then it will come to rest. And if this is just right, so C equals to C critical, zeta equals 1. This springs back in the shortest possible amount of time. Now, you know, sometimes we want things to not oscillate at all, and we want things to return back in the shortest possible amount of time. Is there any application you can think of about this? Yeah, what do you think? Anything? Anyone? Yeah. Recoils in guns. Yeah, yeah. If you have any recoil, that's a very violent one. You don't want your gun to say if you have a spring inside, you don't want that cocking element to oscillate back and forth. Okay, you want it to be straight back in one go. So you want some kind of damping. Or there you go here, Mahmoud has a nice one, automotive suspension zeta equals 1. So if you are driving your car and then you hit on the brakes, you dive, okay? That diving motion sets an oscillation on. If your dampers, if your shock absorbers are the right amount of damping, you dive and then you go straight back up. That's it. If they are under damped, you dive and then you start oscillating, which might be very, okay. Or if they are over damped, you dive and then it takes a long time to return back to.
I was just going to say self-closing door, you know, like the doors you can.
Yeah, that's also another thing. A self-closing door, if that door can oscillate because it has hinges at both sides, and you want the door to not oscillate like the saloon doors, ones that you swing open and then they swing back and forth, you can try to fit in the hinges a good amount of damping so that they close in the shortest possible amount of time without overshooting or without taking an unnatural long time to close themselves. Okay, very good. If the loading is constant changing car, how can you calculate CC? No, you can't calculate CC. You can just approximate. You can have a best case scenario, okay, because you always have oscillation. You can't get it right every time because everything is changing. Okay, so you do it for the average scenario that always occurs, and then you have to live with a bit of oscillation, of course. That's all right. Good. I think we are ready to start the tutorial, which is very easy. That's why I took a bit of time to do these things. All we need is the formula sheet. So all these things that I wrote down so far will be very useful. And we have a did you say 1, 2, and 3? 1, 2, 3. Okay, so question 1. The following data refers to a vibrating system. We have a mass of 5 kilograms, a stiffness of 6,000 newtons per meter, and a damping coefficient of 25 newton seconds per meter. What's that unit? What are these odd units? Where do they come from? C, 25 newton seconds per meter. Oh, of course, you know that C times x dot, C times x dot, this comes from the equations of motion. Okay, so that C times x dot is a force in Newton. So if x dot is meters per second, C is the constant that multiplied times meters per second gives newtons. So it is newtons second per meter. So when you multiply it times meters per second, second and meters go away, and you are left with newtons. So let's do question 1. This will be very easy. Okay, so I will not spend a lot of time on this. We have a mass of 5 kilograms, a stiffness of 6,000 newtons per meter, and a damping coefficient of 25 newton second per meter. We want to find the logarithmic decrement and the ratio of any two successive amplitudes. Okay, so how do we find delta? It looks like delta is a function of the amplitudes, but we don't have the amplitudes. But what we do have, assuming zeta is, assuming this, the formula sheet is on Aula, you go here, tutorial 3, there's vibration formula sheet, just open it up and you find it here. Let me put this here smaller. So what we have is C and C critical. So first of all, from these two, M and K, we can find omega squared. We know that omega n is the square root of K over M. And this gives, do I have a calculator here? Yes, I do. Square root of K over M, that's 6,000 over 5, square root of this, that's 34.64 radians per second. And then with this, we can also find C critical. Remember, C critical is this or this. Okay, we know omega n and m, or we know K and m, that's the same thing. So I can say that C critical is 2 square root of Km, which is equal to K times M is 5 times 6,000, square root of this times 2. That's C critical is 346.41. Newton second per meter, because it's a critical damping coefficient. Well, we know that delta is approximately 2 pi zeta if zeta is smaller than 0.1. So I'm going to make use of this fact by saying that delta equals 2 pi of C over C critical. And that gives, remember, zeta is C over C critical, and that gives, let me check how much is zeta first. Let's not skip steps. Let's find zeta. C over C critical. C is 25 over 346.41. So if I take this, I do 1 over this and times 25, 0.07. 0.072. So this is greatly underdamped. Okay, so it's very lightly damped. The zeta is smaller than 0.1, is smaller than 10%. It's 7% of the critical one. So system is underdamped. And that means that we are in this condition here. So the solution is this one, and it looks like this. And now we can find the delta. Delta is just 2 pi, well, approximately, it's 2 pi zeta. Or you can use the entire formula, which is this one. That's up to you. I'm going to use this one because we have found that zeta is smaller than 0.1. So that's equal to whatever we got here times 2 times pi, 0.453. This delta is no units, and it's no units because it's a ratio. It's a log of a ratio of amplitudes. Okay, so this has got no units. It looks like we have the wrong answer here, but I know for sure that this number is wrong. Okay, I know for sure that the correct answer is this one, 453. How do I know? Because I do this tutorial every year. Okay, so I know. We should change this at some point. All right, so let's find the ratio of the two successive amplitudes. How do we find that? 0.453. This is 0.453. Okay, so that also means that this thing, delta, is also equal to the log of the two successive amplitudes, an over an plus 1. And so how do I find the ratio of the two successive amplitudes? If I take the exponent, if I take the exponentiation of the left-hand side and the exponentiation of the right-hand side, you know that the inverse of the log is the exponentiation. So these two will cancel each other out. Don't do that. Say one is the inverse function of the other. You can't cancel each other out. Okay, if you do the operation, you end up that this, in the end, an over an plus 1 is e to the power of delta. So that means that this is equal to, I take e to the power of this, 1.57. There we go, 1.57, 57 what? 57.3, 57.4, which the solution has at 1.576. That's probably because the solution made use of the full equation of the full thing. Okay, See, very easy, very easy. Just use the formula sheet. You need to find the level of damping to know which equation you need to use. Yes. Cameron, yes. So in the lecture slides, I'm sure that Faris has gave you all three, has gave you three solutions. I'm telling you that the solution to this equation is this only if zeta is smaller than 1. If zeta is equal or greater than 1, you have two more expressions. That's why zeta is very important. You calculate zeta first to understand what's going on, and then you use the correct solution. Now, I believe we don't use critically damped nor over damped solutions anywhere in this tutorial, so there is no way to write, there is no reason to write all the possible solutions. Question 2, a mass of 1 kilogram is attached to the end of a spring of stiffness 800 newtons per meter. So it's a mass of 1 kilogram is attached to a end of a spring stiffness 800 newtons per meter. Determine the critical damping coefficient. So how much is Cc? Then if the damping coefficient is C, 30 Newton second per meter, then determine the transient oscillating frequency. What is that? Yep. So, okay. So what is that? What is the transient oscillating frequency? How did I call it? Omega D. Yes. Thank you, Mahmoud. That's omega D. And determine, compare this with the natural frequency of the undamped system. Which omega is that? Omega n, correct. So we want to find these three things and compare omega D and omega n. We know for sure that omega D will always be smaller than omega n. Why? Because if you look at the equation, omega D is omega n times a square root. Okay? And it's always a square root of 1 minus something that is always smaller than 1 squared. Okay, so this is always strictly smaller than omega n. So help me out. How do we find this? Well, you know that C critical. So see, to find C critical, we don't need C. This is one of the easiest mistake to make. To find the critical damping ratio, you don't need the critical damping coefficient. You don't need the actual damping coefficient. That's the whole point, because you need to compare your actual damping coefficient with the critical one. So you don't need to know what is the actual one. So Cc is equal to 2 omega n m or 2 square root of kn. You use either of these to find Cc. So since we have k and m, I'm going to use the second one. And this is k, so it's 1 times 800 under square root times 2, 56.57 Newton second per meter. That's it. This is Cc. And as you can see, 30 over 56, this is underdamped. How much? Let's find 30 over answer. Is there answer here anywhere? Well, 56.57. 53%. So 0.53. Zeta is how much did I say? 53%. Why do we need zeta? Because we know that omega D is just omega n times the square root of 1 minus zeta squared. And did we find omega n? No, but omega n is very easy. So let me do this later. First, we find omega n is the square root of k over m, which is the square root of 800, which is half as much of this. So 800 under square root, 28.28 radians per second. And so that means that omega d is this, which is 28 times 1 minus 53. Oh, no. So this is 28.28 times 1 minus 0.53 squared under square root. There you go, 23.98. 23.98 radians per second, of course. Okay, sorry, horrible writing. Any questions? As you can see, omega d is smaller than omega n, and it's quite a lot smaller. Well, it's 5 radians per second smaller, but that's just because you have 53% of critical damping. Generally, structures are lightly damped, especially if they are metal structures. They are lightly damped. That means the damping ratio is very small. And that means that omega d is almost equal to omega n. All right, any questions? No questions? None at all? Let's do question 3. A vibrating system consists of a mass of 5 kilograms and a spring of stiffness 480 Newton per meter. Let's do this. Yes.
The question asks you to find the frequencies. I don't know if you want to finish it.
Second. Oh. Sorry, we can get it.
The question 2 asks to find the frequencies. I don't know if you want to finish it or not.
I just found the frequency. Oh, in hertz, you mean? Okay, so these are to 28.28 radians per second, which of course, you know, this is, no, but this is good because I forgot to tell you one other formula that you'll find in your formula sheet, is that omega is always 2 pi times f, where omega is your frequency in radians per second and f is your frequency in hertz. Now, omega is also called the pulsation, okay? So you have the frequency and the pulsation. The frequency is in hertz generally, the pulsation is in radians per second. So this means to find this, you have to divide 28 by 2 pi. Then you get 28.28 divided by 2 divided by pi, 4.5 hertz. And this one is 23.98 divided by 2 divided by pi, 3.82. All right. Yeah, 5.5 and 3.8. Omega n and omega d. I think this means the system is lightly damped. Well, no, you know that the system is lightly damped, is under damped because of this. I would not call this lightly damped. Lightly damped if zeta is smaller than 0.1. If zeta is smaller than 1, you say it's under damped. If zeta is equal to 1, you say it's critically damped. And if zeta is over 1, you say it's over damped. Okay, question 3. Now, you help me out because I got enough already. Vibrating system consists of mass 5 kilograms and a spring stiffness of 480 newtons per meter. And it's viscously damped such that the ratio of any two successive amplitudes is 1 to 0.98. That means amplitude 1 is 1 the amplitude next to amplitude 1, so amplitude 2 is 0.98. So we have that AN over AN plus 1 is 1 over 98.98. All right, this is what it means in in formulae. Determine the undamped natural frequency, the logarithmic decrement, the system damping factor, or damping ratio is also called damping factor. Okay, don't be learn your definitions, because if we ask you for a damping coefficient, it's a different thing than we are asking for a damping factor. Okay, of course, if you're doing the exam, this might lose you some marks. The damping coefficient, as you can see, and the transient oscillating frequency. So help me out. How do I find A, the undamped natural frequency? First of all, which frequency I am talking about? How did we call it? Omega? Omega what? Omega n, correct. So how do I find omega n? What do I have here? You need the stiffness and the mass. We have the stiffness and the mass. So help me out. What's the equation? All right, square root of k over n. So that means we can already do this very easily. Oh. 480 over 5 under square root 9.79. Let's do 9.80 radians per second. And let's do this in hertz because that's what the solution says. So let's do this in hertz, and we have 9 divided by 2 divided by pi, 1.56. All right. The logarithmic decrement. How do I find that? Do I need the critical damping coefficient? I don't think so. Look at what we have already. So damping, we are looking at for the logarithmic decrement. That has to do with damping. And the only information we have on damping is the ratio of two successive amplitudes. Okay. So if you go on the formula sheet, which I'm possibly is this, there you go. If you go on the formula sheet, you look at the logarithmic decrement, it's the log of two successive amplitudes. We have two successive amplitudes ratio. So we just take the log of this to find delta. Delta equals the log of this beast and the log of 1 over 0.98. The log of this thing is, see, I have to use log E, okay, not log 10. You're not seeing it. Is 0, oh, but you don't see anything. That's why. Now you see it. Ah, there you go. Now you see it. I'm using a calculator. 0.02. That's 0.02. It's also horrible now. There you go. And is this correct? Yeah, 0.0202. That's delta, logarithmic decrement. So what is the damping ratio? Cameron is asking, what is the relevance of 1 over r in the equation below the one you just used? If you look at what I told you here, see 1 over r changes if you have non-successive amplitudes. So this is amplitude n, this is amplitude r, amplitudes after n. So since r is 1 in this case, because we have two successive amplitudes, this r is also 1, and so this goes away. All right, let's go back. This we did A, we did B. What is C? The system damping factor. How do I find the damping factor? That would be zeta. How do I find zeta? Having all these things. Come on, come on, come on, come on. Come on, I'll give you a break later. We do this first. Guys.
So that's just the coefficient divided by 2 pi.
Yeah, that's correct. So assuming, we can say assuming that zeta is smaller than 0.1, let's find zeta. Delta is almost 2 pi zeta. So that means that zeta is almost delta over 2 pi, which is delta is 0. This divided by 2 divided by pi, 0.003. 0.003, which is exactly smaller than 0.1. So assumption was correct. We don't need to use the full equation, which is a bit of a mess to rearrange. Remember, if we had used the full equation, this would have been exactly equal to 2 pi zeta over this. Okay. Still, you can do this very easily, but you have to square, you have to use delta squared, you have to rearrange for zeta, take the square root. It's a bit more complicated, but it's the same, don't worry. As long as this is true, though. So we found the damping factor. So let me highlight what we found. We found omega n, we found delta, we found zeta. Damping coefficient. How do we find the damping coefficient now? What is the damping coefficient? What's the symbol? C. How do we find C? Well, we know that zeta is C over C critical. Nice. That means that C is, let's use C critical as 2 omega n m. So that means that C is 2 zeta omega n m. There you go. Very simple. That means that C equals 2 times zeta 0.003 times omega n, which is 9.80, times m, which is 5, 0.294. Newton seconds per meter. Which apparently is not, because it's 0.315 as per the solution. That's because I used 0.003 for zeta. The solution uses 0.00322. Okay, so still basically the same thing. Yeah.
What did that say?
294 Newton second per meter. And finally, the transient oscillating frequency, that would be omega d. And we know that omega d is omega n square root of 1 minus zeta squared. And we know everything. We know omega n. We found it here, 9.80. We know zeta. And so it's just a matter of using your calculator. So 1 minus zeta squared is 0.003 squared. As you can see, it's a tiny number. It's basically 1. This is basically 1 times 9.80. There you go, 9.79, which divided by 2 divided by pi is 1.55. It's 1.56. Hey, look, it's the same. Look, it's the same. Why is almost the same? It is almost 9.80 radians per second, which is almost, of course, 1.56 hertz. Why? Because the damping ratio is ridiculously small. So 1 minus zeta squared, this squared is a tiny number. 1 minus a tiny number is 1, and the square root of 1 is 1. So omega d is almost equal to omega n. So for the 2 digits approximation that we have used, it doesn't make any difference whatsoever. There you go. You have earned yourself a break. Well, I earned a break because I did most of the work. Okay. Any questions? No questions? So this is easy. Do you agree with me? This is not that hard. Okay, good. Because next hour we are doing forced vibrations, and we'll see how to use everything that we learned to apply to a mechanism or problem, so an oscillatory problem. After this, it's way easier. Okay. Yes. Question.
What are the units on the phone?
The units of
The last.
1.5 hertz. So I'm saying it's just 9.80 radians per second. If you divide everything by 2 pi, as I said, you get hertz. Is it really so unclear? There you go. All right, so I'll give you 6 minutes break. Okay. So I'll see you at noon sharp. Students online, any questions? You pop them in the chat, please. I have it open. And I'll also pause recording. Okay, recording is now resumed. Guys, hello. Stop. Please, eyes on me. Thank you. I want to, before we start the second part of this tutorial, I want to have a brief recap of the second part, the second half of this formula sheet, which looks very confusing and looks ginormous. Look at this. Wow. So I want to show you where all these things come from first. So let's start with a bit of theory. The theory is always the same. You have the same system. As before. But now there is an external force. And this external force, as a function of time, let's say for ease of this, it can be anything, okay? But the easiest thing it can be, other than 0, of course, is a sinusoid. So let's call this F0, which is the amplitude of the sine wave of the forcing function, sine omega t. Notice I am using omega. I'm not using omega n. Omega n is a property of the system. That's it. As long as it's got k and m, omega n is defined in place. It's there. It's a property of the system. Omega is the frequency, the pulsation of the external force, which can be anything. Now imagine this pencil here that is in my hand. If I tap it, it will vibrate at a certain frequency. Okay. Now for free vibration, it vibrates at its own preferred frequency, which is the natural frequency of the system. It's called natural frequency because if you let it go, it vibrates at this preferred frequency. It prefers to vibrate at this frequency here. Okay. Now let's apply a force. If I apply an external force of 3 hertz, say like this, what's the frequency of vibration of this pencil? It's 3 hertz because I'm forcing it. So the solution will generally not contain the natural frequency of the pencil, but will contain the external forcing frequency. Okay? So the solution is different. And is different in a particular way. So let's write the equations of motion. First is mx double dot plus cx dot plus kx, but instead of being equal to 0 now, it's equal to the forcing function f of t. Well, in this case, let's use f0 sine omega t. Now, the solution of this equation is the sum of two different solutions. We call it the general solution plus the particular solution. The general one is the solution of the associated homogeneous equation. The homogeneous equation is this one. Does this remind you of anything? Yes, we know the solution of this already because we did it just now. So this is the homogeneous equation. The associated homogeneous equation, and the solution x of t is the solution of the homogeneous equation of t, which we know, plus the solution of the particular integral. That's how we call it. It looks like very complicated because this thing, remember, is a e minus zeta omega n t sine omega d t plus phi. So this thing is this, and this thing here depends on what's on the right hand side. Okay. Now for a right hand side like this, xp of t is capital X sine omega t minus theta. Capital X is something that we are going to discover now. It's an amplitude, of course. And this is just a sine wave that is lagging. It's a lagging sine wave. This is the response, and it's lagging the force because of cause effect. The force comes always first. There is no way that the mass can anticipate the force. It's the force that drives the mass, not the other way around. Okay, how much is capital X? Well, capital X is, again, this only works if the force is a sinusoidal force. Capital X is F0 over K divided by the square root of 1 minus rho squared plus 2 zeta rho squared. Again, this is a beast of a solution. This must be substituted with this. What is rho? Well, rho is just omega over omega n. What is omega? What is omega, guys? Of what? Look at the equation. Where is omega? It's in the force. Omega is the forcing omega. Omega n is the system natural frequency. They are completely different things. All right? This is very important. This is critical. Once you understand this, it's very easy. What about that theta? Well, theta is the arctangent of, basically, this is a triangle. You can visualize this as a triangle. This is the Pythagoras theorem of a triangle with this edge and this edge. And so this is opposite and this is adjacent. So you have that theta is 2 zeta rho over 1 minus rho squared. There you go. I know this by heart. Okay. Not because I know this by heart, because, well, one thing is because I do this every year. That helps as well. But also because I know physically what all these things mean. So I can back up the formulae, even if I don't know them. What's under the second bracket set under the root? Here, 2 zeta rho. 2 zeta rho. Zeta is just C over C critical, and rho is this. It's just a way to avoid writing this other beast, which is exactly the same thing, F0 over K, 1 minus rho squared plus 2 zeta rho squared. So this makes it neater to write. So it looks nicer. All right? Yes.
What did you say was the difference between
Omega is the force, is the frequency of the force. It's here. Look, it's here. Omega n is square root of K over m. So that depends just on the mass and the stiffness of the system. The external force is external. It can depend on anything else. It can depend on anything. So omega of the force is completely distinct from the omega n, which is also, but it's related to the omega d, which is the damping omega. Now, let's look at the full solution, which is this. This is this beast that we found earlier that contains omega d and contains a decaying term, plus this beast that contains this other beast and this other beast. Okay, it looks very complicated, but what happens here? Have a look. What is this? What is that? A decaying term. If time goes to infinity, what happens to this term? Oh, for time going to infinity, e to the power of minus infinity tends to 0. So this thing disappears completely. So we can say that this is the solution, but at steady state, so after enough time has passed, the solution is just this. Okay? Because this term decays very quickly, decays exponentially. So I can say that at steady state, x of t is just xp of t. Okay? So it's just the particular solution, which is just a sine wave. See, this doesn't decay. Why doesn't this decay? Because I'm keeping forcing it. If I force it, it never decays. I keep pumping energy into the system from the external environment. That's it. That's it, really. That's all you need to know. Well, you might want to know what does this look like? So what does this look like as a function of omega? Well, if you have this as a function of omega, x and theta, how do they look like? Let me do this. Let me put this here. No. They look like this. Let's say that this one is omega n. And then we have theta here that looks like this. This is 0, this is 90 degrees, and this is 180 degrees. Of course, this is minus 90 and minus 180. Okay. And this is what happens. Look, what happens if zeta is 0. So this is no damping. When zeta equals 0, see what happens? This amplitude, sorry, this amplitude, x, this is a constant. Zeta is 0, so this goes away. 1 minus rho squared. Rho squared is this. If I change the forcing omega, this is the forcing omega. If I force very lightly, I get a vibration. If I force it just at the right frequency, everything explodes, basically. It explodes because you have infinite amount of amplitude. This is an asymptote. See? 1 minus 1, because if omega is equal to omega n, rho is 1. 1 minus 1, this is 0. Square root of 0 is 0. This over 0 tends to infinity. So if you don't have damping and you excite a system at its natural frequency, you have a tiny force produces infinite amplitude. And that is bad. That is very bad. So what happens if we have damping? Well, if you have damping, this becomes like this. Okay. And if you have more damping, this happens. What happens to theta though? Well, theta has this sharp turn. If you have no damping, see what happens here? No damping, 0 over 1 minus rho squared. So 0, then this changes sign, and then bam, minus 180. Okay. If you have damping, this happens. If you have more damping, this happens. If you have more damping, this happens. Okay, so it gets easier and easier as you add damping. What can you observe here? At the natural frequency, if you force at the natural frequency, the response is 90 degrees out of phase, always. Okay? And now a question, looking at this plot. If you have damping, is the largest frequency, is the largest amplitude associated with the natural frequency or not? What do you think? It's not. It's not, because see, I did this on purpose. Look at this. If I increase damping, the largest amplitude goes down and down. Okay? They coincide only if there is no damping. So if there's no damping, the largest amplitude you find at omega n. If there is damping, the largest amplitude you find at the difference omega. That different omega, we call it resonant frequency. Okay, so resonance, natural frequency, damped frequency. Make sure you learn the definitions. If I say at resonance, it doesn't mean when omega equals omega n. It means omega r is omega n times 1 minus 2 zeta squared. Okay, So this is another thing that you have to remember. This is the resonant frequency. And it's here. See? It's here. It's here because omega is omega n when phi is 90. And then you have that at omega equals omega r, which is equal to this, which I just wrote here. You have the largest amplitude, which you can also write like this. So this peak here, this peak is always f over k divided by 2 zeta times square root of 1 minus zeta squared. Okay, you find it by just looking at this equation. See, you look at this equation. If omega, this here, if omega is equal to this omega here, you have a maximum of this function. All right. Another thing that you can do here on this plot, and it's the last thing I'm going to show you. Another thing you can do on this plot is to find where is the omega that gives 45 degrees. Look at this. If I say this is minus 45, and this is 135, minus 135, I can intercept this, and I can intercept this. So these two omegas, which are changing with damping, look, this omega here, omega 1, and this omega here, omega 2, they define how much the peak is shallow or not. Okay, so if you take this omega 2 minus omega 1 divided by 2 omega n, it gives you an estimate of zeta. So we found another way of estimating zeta, the ratio of two successive amplitudes, C over C critical, or if you have this information, omega 2 minus omega 1 divided by 2 omega n. Omega 2 is where this curve intercepts 135 degrees. Omega 1 is where this curve intercepts 45 degrees, and omega n is always omega n. So as you can see, for these ones, you have a different omega 1 and a different omega 2 because you have a different damping ratio. If you change damping, you change where these curves intercept 45 and 135. All right, now that we know everything about resonance and everything about forced functions, we have discussed the ins and outs. Let's solve a tutorial question. Which is not this, not this. Sorry, which one was it? Question number 2. Oh, 2 and 3. Okay, so system in figure 1, which is this one, is subjected to a sinusoidal force of constant magnitude 800 newtons. The amplitude at very low frequencies tended to 8 millimeters, and the maximum amplitude was this. Determine the natural frequency, the damping factor, and the support stiffness. Now, something that I didn't show you, which can be also very helpful, is what happens if this forcing omega goes to 0. Look at the equation. If omega goes to 0, so it means I'm not forcing it. Well, there is a force applied, but it's a static force. So look, this is the equation. So F0 times 0 times sine of 0, that's just F0. So it's a force that does not oscillate. What happens if I apply a force that doesn't oscillate? This becomes a statics problem. And statics problems, what is X? If I know F, and I know X, how do I find X if I know F divided by K? Okay, that's the idea. In fact, if I'm not forcing this, omega is 0. Let's see what happens. This becomes 1. This becomes 0. This is square root of 1. There you go. X equals F over K, or F equals KX. See how everything checks out in the grand scheme of things? So that means that this tiny distance here, that let me mark it as this distance here, which is where all these curves converge when they are 0, this is just K. That's it. Okay. So let's make use of this fact in question 2. So this is DTS 11. Question 2. Guys, you have to let me know if you want these summaries or not. If they are useful for you or they are not. Okay, because I know that they take quite a lot of time of the tutorial, but I also think that they are useful because if we just crack on with the tutorial without having the summary first, some of you might feel lost. Okay, and also these are also useful to me because I get all the formulae I need on paper first, and then I use them. Okay. Yeah, Adnan says they are useful. Thank you. Yes, Maggie as well. Yes, I believe so. So question 2. So the equation of this thing is basically what we are saying is that f of t is 800 times sine of omega t. I don't know how much is omega. But we know that the amplitude at very low frequencies, tended to 8 millimeters. So I know that X, capital X, that's the amplitude. We know it's the amplitude because we are saying at steady state. So this, we are neglecting this. So this X at very low frequencies, that means when rho is almost 0, so this denominator is 1, X at omega equals 0 equals F0 over K. Agreed? This is what we find from the equation. And we know that this thing is also 8 millimeters. So it's 8 times 10 to the minus 3 meters. And the maximum amplitude, we know that X, where is the maximum amplitude? At which omega is the maximum amplitude? Look, omega n. Correct. Omega r. Okay. So X at omega equal omega r is 10.91, so 10.91 millimeters. And we also know omega r because it tells us that that amplitude was captured when the force was at 82.5 hertz. So we know that FR is 82.5 hertz. I'm calling it FR because it's in hertz. If we want omega r, we have to multiply this times 2 pi. All right, determine the natural frequency. How do I find Fn? Knowing all these things. Well, let's go back here in the formula sheet. And you know that the amplitude when omega is omega r is this beast here. So I can say that capital X, where omega is omega r, is f0 over k times 1 divided by 2 zeta square root 1 minus zeta squared. And so this is a number. So I know, do I know zeta? I don't know anything, but I know I can find k. Right? I can find k from here. So first I find k. From here I say k is just x over f0. No, sorry, f0 over x. Which is equal to 0.08 divided by 800. No, 800 divided by this, 100,000. It's 100,000 Newton per meter. So this is K. Now we need to find omega. What's we want? What do we want? It's not this. It's this. We need to find the natural frequency. Well, we know that also, we know that Fn, if you want to write it, Fr is Fn square root of 1 minus 2 zeta squared. So what's missing here is zeta. Well, we can find zeta from here. Look at this equation. How many unknowns we have here? Well, F0 is given. So F0 is 800. K we just found. This thing on the left is this. So the only unknown here is zeta. So without knowing anything, just by looking at the formula sheet, I can find zeta. So if I square everything up, I get x squared equals f0 over k, f0 squared, 1, 2, zeta squared times 1 minus zeta squared. And so I get that zeta, so zeta squared minus zeta to the power of 4 equals f0 squared over k squared x squared divided by 2. Do you agree with me? Did I get this correctly? Second? No, this zeta squared times this and zeta. Oh, I'm missing. No, it's fine. That's fine. I think it's fine. So this is, let me put this on this side. And so I can rewrite this equation as zeta to the power of 4 minus zeta to the power minus zeta squared plus this thing, which is a number. This is just a number. Equals 0. And this is a quadratic equation. Okay, we can solve this with Wolfram alpha if you want. So this has two solutions. One of them is negative. So one of them is useless. Okay, can you solve this for me, please? I'll try to do this with Wolfram alpha, see what happens. Is the 2 not supposed to be squared? Yeah, probably. Let me check. Oh, yes, of course. Thank you. So this is 4. Oh, this is what you were trying to say. Okay. All right. Thank you very much. So it's 4. Cheers. Wolfram alpha. Wolfram alpha. Again, you should do this by hand, though. Okay, I'm not doing this by hand because I'm lazy. So x squared, let me call this x. Let me call it y. Y squared minus y. Well, you can also do this, it's fine, it's the same thing. So you can turn this equation. How do you solve this by hand? You turn this equation, let's call this lambda. Let's say that lambda is zeta squared,
Substitute
and then you substitute.
this squared for, well, let's say u, and then for the whole thing at the
Yeah.
last time you just put a or something,
Yeah.
and then do it, and then substitute it later.
Okay, so you solve this one. So this is a quadratic equation. This is a, b, and c. So square root of b squared minus 4ac. Oh, that's one thing. I'm going to do this plus 0. So let me call this c. So if you solve this, you get this. Let me do this. Let me do this. So the solution is this one. Y, so lambda squared is, lambda squared 1 is 0.5 of square root 1 minus, so 1/2 of 1 minus square root 1 minus f0 squared divided by k squared x squared. There's times 4, but then I can just simplify the 4 there. Okay, so this is the square. So this is also, sorry, this is lambda 1, which is zeta squared. Lambda 1 is zeta squared. And so that means if I wanted to find zeta, is just take this. And this is the square root of everything. Okay, there you go. This is a number because this is 800. This is 100,000. And this x squared was 10.91 times 10 to the power of minus 3. Right? You do this. Question, guys, is this overwhelming? Should not be. Should not be. Okay? You need to practice. That's the whole idea. I know it might seem overwhelming. That's because the lecture was just yesterday. So you didn't have time to assimilate everything yet. But it is not very hard. Okay, it's just algebra. It's just mathematics. Okay, we found zeta. So this is a number. This number is, let me find it in the solutions. Damping factor, 0.4. This is zeta is 0.4. Okay, so do we find the natural frequency? Yes, it's very easy. It's here. Fn is Fr, which is this, divided by square root of 1 minus 2 zeta squared. Very easy because zeta we just found. Everything else is easy. So Fn is Fr over this. Which is equal to 100 Hertz. And the support stiffness, which is what we found earlier. So this is also a result, is 100,000. It is 100,000 newtons per meter, which is 100 kilonewtons per meter. All right. What do you think? Takes practice. It's just formulae. You have to be comfortable with the mathematics and the algebra. That's all there is to it. As long as you understand what's going on, you understand what's going on here, and just you understand what's going on here. It's just a matter of applying the correct equations. Okay. Question 3. Question number 3. Number 3. Let's see what time it is. Oh, it's 20 to 1. We still have 20 minutes. How time flies when you're having fun. So question 3. A structure which can be modeled as the system shown in figure 1, which is always the same, was given a small displacement from the static equilibrium position and released. Is it the same? Yes. And released. Where it is? Oh, it was observed that the transient frequency was 33 Hertz and the amplitude attenuated by a factor of 9.2 each complete cycle. Ooh, wow. If the mass of the structure is 100 kilograms, determine the damping factor, the undamped natural frequency, and the support stiffness. The amplitude and phase of the amplitude relative to the excitation force when subject to a sinusoidal force. Oh, there you go. Ooh, wow. All right. So this first part, to me, all this first part looks like free vibration. See, I am giving a small displacement from the static equilibrium and releasing. That means there is no external force. So what do I use? Do I use this? Do I use these? Or do I use this? Okay, of course, I must use this one. Because what's happening right now is that I am displacing something, releasing it. So this vibrates freely, and it vibrates at its own preferred frequency, which is omega d. Omega n if it's undamped. But we know that it's got damping because the amplitude is attenuated every cycle. Every cycle, the amplitude goes down by a factor of 9.2. So let's do this very briefly because this is what we did already. So the transient frequency, that's omega d. So in this case, FD, because it's in hertz, 33 hertz. And the amplitude has attenuated factor 9.2 each complete cycle. That means that AN divided by AN plus 1 is 9.2. So the previous oscillation is 9.2 times higher than the successive oscillation. If the mass of the structure is 100 kilograms, determine the damping factor. How do I find the damping factor? Come on. Zeta is logarithmic decrement divided by 2 pi, which is the logarithm of AN over AN plus 1 divided by 2 pi. This is provided that zeta is smaller than 1, which in this case it's not. It's 0.333, so that's up to you. Okay, so just find zeta using the larger equation. This is equal to 0.333. Found. Undamped natural frequency. How do I find the Fn? Well, Fn is Fd divided by the square root of 1 minus zeta squared. Zeta we just found, Fd is there. So this is equal to 35 hertz. Easy. Support stiffness. How do we find the support stiffness? Well, we know the mass, we know the natural frequency. We know that omega n is square root of k over m. And so that means that k is omega n squared times m. And so that k is also equal to omega n is 2 pi f. So it's 2 pi fn squared times m. Fn is given. Fn we found. the mass is given. There you go. K is equal to 4.836 million newtons, meganewtons per meter. Oh, now we do the actual forced stuff. The amplitude, we want to find the amplitude and the phase of the amplitude relative to the excitation force when subjected to a sinusoidal force of magnitude 100 Newton and frequency 35 Hertz. Look, if I look at this frequency response function, okay, so this is omega n, and this is omega r. Agreed with me? Because it's damped. We know that every oscillation it gets attenuated by a factor of 9.2, so there is damping. So the max amplitude is not happening at omega n. And well, of course, if I divide everything by a factor of 2 pi here, I can just say f. Instead of saying omega n, I use the frequencies. It's the same thing. I'm just rescaling by 2 pi. Okay, so what do I want to find again? The amplitude and phase. So I want to find x, and I want to find, remember, theta. And theta is this, which in the damped case is this. Okay. Want to find f and the phase. You know, this is 90 degrees, minus 90 degrees. When f, the forcing function, the forcing, where is the forcing? Yeah, the frequency of the force is 35 Hertz. But 35 Hertz is the natural frequency. Fn is 35 Hertz. So the external force excites the natural frequency of the structure. That means we are here in terms of amplitude, and we are here in terms of phase. Without doing any calculation, I can tell you the phase is minus 90 degrees. It must be. But I still need to find x. How do I do that? I copy this. And I put numbers in. There you go. I copy these ones. F0 is 100 newtons. K is given. Well, K is this. What is rho? Rho, remember, is omega over omega n, which is also f over fn. Agreed? Because it's divided by 2 pi on both sides. The 2 pi goes away. So f is 35. Fn is 35. So rho is 1 in this case. Zeta is 0.333. And so x is just 100 over 4.836 times 10 to the power of 6 newtons per meter, divided by the square root of 1 minus 1, 0, plus this is 2 zeta squared, which is 4 zeta squared rho squared. Agreed? Which is just 2 zeta rho in the end. Let me do this. You put this first, F0 over K, and this is 2 zeta rho. Agreed? Because rho is 1. So in the end, I get, well, just need 2 zeta because rho is 1, as I said. So this is equal to 100 divided by 4.836 times 10 to the power of 6 divided by 2 times 0.333. And if you do this, you get that x is 0.031. How is rho 1? Well, rho is 1 because f is 35 hertz and fn is also 35 hertz. It says here, the forcing function is 100 newtons times 2 pi 35 times t. So 100 Newton at 35 hertz. What I'm saying is that f of t is 100, 2 pi f, 2 pi 35. Okay. And it's 2 pi 35 because omega t. Omega is 2 pi f, always. Remember that? Does this make it clear? Online? You? Yeah, good. So this thing is apparently 0.031 millimeters. Because it's here. I'm just looking at the solutions. And as I said, the phase is 90 degrees. It must be 90 degrees because at Fn, the definition is that's 90 degrees. Look, we can also see it here. If you look at this, if rho is 1, okay, this is arctangent of infinity. Where is the arctangent infinity? Pi over 2, which is? Ta-da! 90 degrees. Yes.
Why is a rho equal to 1?
I just told you. It's here. Look at this. Fn is 35. F is the forcing function is 35. Okay. So this is the external force. External force is 100 newtons at 35 hertz. Now this happens to also be the natural frequency of the system. So we are exactly here, which is not the peak, but it's where the phase is 90 degrees. All right. Finally, last thing, and then I'll let you go. What's the resonant frequency and the resonant amplitude if the amplitude of the excitation force remains constant? Okay, so what's the resonant frequency? Well, that's very easy. Once we know that Fn is 35, Fr is Fn times the square root of 1 minus 2 zeta squared. That's not Fd, this is Fr. And so you can find that this is 30.88 hertz. And so we are here, look, we are now here at a lower frequency. And the amplitude is, of course, higher because I told you the amplitude is higher. And the amplitude, you do it in the same way. Now, rho is different. Because if you are here now, rho is Fr over Fn, and then you get a different amplitude. So x, when F equals Fr, is 0.033 millimeters. And you can, if you look at the formula sheet, you have it here very easily. If x of F equals Fr is just this. And look, at omega n is F over K is F over 2K zeta, which what I got here. See, I've applied the formula from scratch, but if you look at the formula sheet, it's already there. All right, you don't have to do anything. And this one, I can go here and substitute everything from scratch again, or I can just go here and say, okay, it's just F over K divided by this other piece. All right, good. I'll stop this recording. In the meantime, have you got any questions?